In this video, we are going to take a look at the pH scale and calculating pH from some concentrations. So just a little bit about the pH scale. If if you ever see a p, a lowercase p, in a chemistry class or a probably any science class for that matter, little p normally stands for something called the negative logarithm. Now these are base 10 logarithms, so these are the ones that you can just straight plug into your calculator and get your answer. But anyhow, so if we're going ahead and write a formula for calculating pH, it's going to look like pH is equal to the negative logarithm of the hydrogen ion concentration. So I'm going to put H plus in brackets. Alright, so I know this sounds like a mouthful. pH is equal to the negative log of the hydrogen ion concentration. So if we look at this, this H stands for the hydrogen ion concentration. So an acid, when you put it in solution, it will make either a hydronium ion, which is H3O plus, or we say it makes a hydrogen ion. But if you look, the only difference between these two is a water molecule, an H2O. So if I have water and I have H2O and I add a hydrogen ion to H2O, so if I add this to water, it becomes H3O. So a lot of times when you're talking about acids, you're going to see this term H3O plus and you're going to see H plus, and for our purposes they're basically interchangeable for one another. They both mean acid. It means that you've got this acid concentration or this acid that has been made in solution. And wow, it's really raining pretty hard outside. I don't know if you can hear it on the roof, but anyhow, it's raining. So pH, if we look at pH, pH, if you'll recall, is basically a scale that ranges from 0 to 14, with 7 being in the middle. And if something is 7, it has a neutral pH, or basically it's just in the middle, so it's neither acidic or basic. If something has a pH number of less than 7, it's considered an acid. If something has a pH number of greater than 7, it's considered a base. The further you are from the middle point, which is 7, the stronger your acid becomes. The further away from the middle point of 7 that your base has, it becomes a stronger base. So for example, let's choose a different color here. So for example, if I had an acid that has a pH number of 3 versus a pH number of 4. If we will look at this, 3, that's a 3. So 3, let's erase that. That 3 doesn't, oh, that's not what I want. So let's see, let's do a black. Well, that's still not what I want. Well, anyhow, that is a 3. So we're going to do this. So that's a 3. So if I've got a 3, that's further away from 7. So this is going to be a stronger acid compared to something that has a pH of 4. Whereas on the other end of the scale, if I've got a solution with a pH of 12, say versus a pH of 13, the solution with the pH of 13 is going to be a stronger base because it's further from 7. Alright, so we're going to take a look at a problem, and we're going to use this formula to solve. So let's go ahead and scroll on down and look at our problem. So it says, what is the pH of a solution that contains 19 grams of hydrogen chloride dissolved in 1.5 liters of water? Well, the first thing we're going to do, it says, what is the pH? So we know that's what we're looking for. So I'm going to go ahead and write out my formula. pH is equal to negative logarithm, negative log for short, the negative log of the hydrogen ion concentration. So whenever you see brackets, you don't really treat these any different than parentheses per se. They're just another way of kind of showing some organization. But so don't let the brackets kind of freak you out. They basically mean the same thing in this sense as parentheses would have. But let's go ahead and start plugging in some things. So pH is what we're looking for. So pH is equal to negative log. Now, we have to find this hydrogen ion concentration. So you may say, okay, how do I find the hydrogen ion concentration? Well, basically, whenever you have a strong acid, and we know that hydrogen chloride is a strong acid, it means that it fully dissociates into solution, okay? So, a strong acid, because it fully dissociates in solution, whenever we calculate the molarity of a solution with a strong acid, the molarity is going to tell us what the hydrogen ion concentration is going to be. Now later on, if you go into higher levels of chemistry and you look at weak acids and things of that nature, you'll do more in-depth calculations with this. But just for right now, we'll just assume that hydrogen chloride being a strong acid, if we can figure out what the molarity of the solution is, that is going to tell us what the hydrogen ion concentration is going to be. So if you'll recall, the formula for finding molarity is equal to moles of solute divided by, so let's see, so moles of solute divided by liters of solution. So moles of solute divided by liters of solution. So let's go ahead and plug in some numbers here. Okay, so moles. So if I look up here and it says contains 19 grams. Okay, so we know we've got grams and they want moles, so we have to convert grams into moles. So before I can even finish this, I have to figure out how many moles is 19 grams of hydrogen chloride. So let's choose a different color here. Let's use the kind of teal color. So I'm gonna write it, fit it under here. So 19 grams of HCl, and we want to find out how many moles that is. So I'm going to put that over X moles. I'm going to set up a ratio. So I'm going to say 19 grams of hydrogen chloride will give me X moles. And to find the molar mass of hydrogen chloride, I take the mass of hydrogen and add it to the mass of chlorine, which is going to give me 36.45 roughly. 36.45 grams of HCl will give me 1 mole. So that's the number that we're going to use for the molar mass. So if you add the chlorine and add the hydrogen together, you get 36.45 grams of hydrogen chloride. So scrolling on down, to solve this, all that we need to do is cross multiply and divide. So after I cross multiply and divide, and I solve for x, I'm going to find that x is going to equal 0.521 moles. So I've got 0.521 moles of hydrogen chloride. So I've just rounded to 3 decimal places here. Usually, it's best if you don't round until the end. If you just keep the number that you get in your calculator and use your recall function or your memory function, that way you're not having to punch in 8 or 9 different digits at a time. But it's best not to round until the very end. Because these problems, some of these problems you'll do include 2 and 3 steps, and if you're rounding at each step, you're throwing away part of the number, and by the end, your final answer may be significantly different than what you should have gotten. But anyhow, we're going to say 0.521 moles of HCl. So now we're going to take this number and we're going to plug it into this formula up here. So the molarity formula, if you recall, was moles of solute divided by liters of solution. So let's take my 0.51 moles of HCl, so that's our solute, moles of HCl, and now I'm going to divide that by liters of solution. So if you will recall from the problem, we had this dissolved in 1.5 liters of water. So that's what I'm going to put in the denominator of my molarity formula. So 1.5 liters of water. So I'll just put H2O here. So now when I take 0.521 and divide it by 1.5, I'm going to get a molarity of 0.348. Now once again, I've rounded to 3 decimal places here, but when you're doing this on your calculator, you should not round at all until the very end. So now I've found out the molarity of this solution. So if you recall from up here, we said if we can find out the molarity, that's going to tell us basically what the hydrogen ion concentration is. So now we take this number and we plug it in over here to this formula. So I'm going to say go back to my red here. So negative log, I forgot my negative. So pH is equal to the negative log of the hydrogen ion concentration, which is going to be this number, 0.0348. So we're going to say, or 0.348. 0.348. All right. So now once we take the negative log of this number, we are going to get 0.45, and that is our final answer. This is what we're looking for. So this is the pH of the solution. Now, if you recall, this is definitely less than 7. So we had 0 to 14 on the pH scale, where 7 was in the middle. 0.45 is definitely well below 7, and it's a good bit below 7. So we know that basically this is a very strong acid because it's very far from 7. And there's our pH, 0.45.